Good time of the day, everyone, and welcome to the EPIC online technology meeting on Photonics chips for AI. This is one of the series of our online technology meetings that cover different aspects of photonics. And let me remind you that it's provided to you by EPIC, the European Photonic Industry Consortium, that is the largest industry consortium in photonics in the world, having over 800 corporate members centered around Europe, but also all over the world. Today we have a very exciting agenda, and we have 6 speakers that will talk about different aspects and different developments in the field of photonic integrated circuits for AI. We will hear from CORNERSTONE, Itronics, Photon Poser, Pilot Photonics, Proud Technology, and PHIX, all of them proud members of our EPIC community. And apart from them, we have a great audience today with us. We have over 100 registrants from all levels of the supply chain in the photonics industry. We have representatives of the end users and integrators, material producers, equipment manufacturers, metrology and testing, service providers, contract manufacturers and foundries, consultancies, and different components and models, and of course plenty of R&D institutions joining this meeting today. So I welcome you to join the discussion, and I hope this will be a very fruitful meeting for all of you. So as always, we target to create new collaboration opportunities inside our industry. So without further delay, I'd like to introduce our first speaker, that is Frederic Gardes. So Frederic represents CORNERSTONE, but he is also a professor at the University of Southampton. And Frederic will talk about photonic chips for AI and more or less introduce us to this exciting topic. Welcome, Frederic. Good to have you with us. I'm just going to share your slides right now.
Thank you, Ivan, for the introduction.
The floor is yours.
Yeah, I've got a couple of hats today, and I will first talk a little bit about the Cornerstone activity and what we can offer to the community, and then I'll talk a little bit about the research, in the background that we do as well, and some of the components and potentially systems that we are developing, and you can also develop on the Cornerstone platform. So next slide, please. So in Cornerstone, we offer a range of MPWs, as you perhaps know, and the technology platform varies between standard SOI with different thicknesses to silicon nitride, which offers like 2 different thicknesses these days, because we also look at visible potential systems. And we also have like some germanium on silicon, which really focus more on the mid-infrared activities. And as part of other developments, I would say, we also have like some integration capabilities where we can do flip chips and light sources on your chips, some PDs or electronics that we can also bond, and we also offer different services in terms of lithography and e-beam, depending on your requirements if you have some dedicated needs. So that being said, we have like a range of MPWs that are coming up in silicon on insulator. 220 the passive and the active. The active, I'll show you an example of what we did in neuromorphic a couple of years ago, which was quite successful, and that's standard PN junction modulators type of system. When we also have like some silicon nitride coming up, and we have something called the student batch where you get that single edge and reduce cost. One key point of Cornerstone, we have this open platform type of environment where it's an open source PDK, so you can have access to all the designs and all the components, and you can actually use all the ecosystem that is available to you in order to actually develop this further. And there's no attachment to this in terms of IP, so it's free to use. Next slide. All right. So we also do something called a PHIX bootcamp. So that's quite interesting if you are quite new to the photonic environment and you want to know a bit more about how things are fabricated and how they are designed. So we run a boot camp next year at a number of occasions that you can see here. If you're interested, just click on the link. But essentially, you come here and you have like interaction with different ways of designing these chips and how we actually do the fabrication and the measurements. So this is quite an interesting training that we do and we run quite regularly actually. So feel free to click on that. Now, I wanted to use my second hat and to show a little bit of the research and what we use Cornerstone for and what we do beyond Cornerstone, because we also do our own activity beyond Cornerstone. Next slide, please. So as you know, computing is really power hungry, and we're talking about nuclear power station to run data centers these days. And literally trillions of dollars to actually feed the infrastructure or even develop it. So this is exponentially increasing. So we need to do something, and this is why we're talking about these things in photonics, I suppose, and all sorts of other activities in neuromorphics as well. So next slide, please. And the point of all of this is really to find ways to get this, to see what silicon photonics can do. And there are two ways to look at this, right? There is like the data transfer, which is, sending data at the highest bandwidth possible for the lowest amount of energy. And there is also like trying to achieve computation using photonics, right? So I'll just touch a little bit of both topics today. So next slide, please. So one of the key points in photonics compared to electronics, so just to try to take a step back, electronics, the problem with electronics is like you have extremely high density of devices, and you can do a very, very fast computation in parallel using GPUs, but the memory is not where the computation occurs. So you need to have data transfer between your memory and your compute constantly, right? So that costs power, that costs latency. And it's a bit of a bottleneck that photonics doesn't really have, and any analog circuit, I suppose, doesn't really suffer this kind of a problem, because the point of photonics is you can pretty much compute at the speed of light. So your light propagates into a system, and you see like different weights or that impact the phase or absorb the light along the way, and you can actually do computation using the devices that I'm showing here. So you can do that in free space using Mach-Zehnders on the chip that gives you this weight matrix multiplication. You can do that in a non-coherent environment with different sources and ring resonators, and so on and so forth, right? So the idea is always the same. You propagate your light, you have the memory as you propagate, and you try to do computation as you go along. Next slide, please. So here is an example of what we did with some of the Cornerstone active runs. So this is SOI 220 active, for instance. And the point of this was just to demonstrate that using a coherent system and PN junction modulators, we could achieve like literally a rate that was way in excess of what, for instance, NVIDIA could produce, right? With quite a good accuracy as well. So one of the problems with analog type of computation is noise, and that affects your accuracy. And how do you deal with that? This is a complex problem that needs to be addressed. And I think we had a bit of a successful system here where we cascaded like different type of Mach-Zehnders and we try to achieve this coherent photonic neural network. If you're interested in knowing more, you have like the link, and I think the slide will be shared, so you can have a look at this. And this was fabricated with the further active runs in Cornerstone. Next slide, please. So one of the key points that I wanted to make here is, photonics is all about trying to catch up with density of integration, I suppose, that you have in electronics, and it's quite sparse compared to what you have in electronics. So how do you actually achieve that? So you have a plot here demonstrating that you can really increase this density of integration, I suppose, recently. And the other problem is loss on the chip. So you lose a lot of the light as you stack up your devices. So you need amplifiers on chip eventually, right? So these days you have like MTP bonding, you have die bonding, and what I wanted to introduce here is one step further, monolithic integration of stratified and silicon. So instead of bonding stuff and playing Lego a little bit, I would say you grow things in line, so you don't have to actually rely on any other fab, and that would become part of a process line basically. So next slide, please. So this is just like an introduction slide that, you know, I think John Bowers came up with that little ladder step. But essentially, you want to have like your laser grown on silicon, and you want to be able to couple that efficiently to a waveguide, right? And so far, you know, you have mixed results on this. And one of the big problems is not actually to grow the laser on silicon, is to couple it to a waveguide efficiently and at wafer scale. Next slide, please. So we came up with a bit of a process that we can scale up to 200 millimeters and potentially 300. And we tried it with something called the quantum confined Stark effect modulator in the O-band. So that's, you know, kind of fitted for like data centers. And the problem with those devices, they're quite sick, right? A micron plus. So how do you actually interface that to a waveguide system that is compatible with, you know, CMOS type of system? So silicon or silicon nitride. And this is exactly what we've done here. So you have this thick, you know, stack that you see in the middle, and you try to couple that to a silicon nitride waveguide, and you can see cross section, you know, at the bottom right. So you transfer the light from one to the other, and that works with silicon germanium. So next slide, please. And that gives you extremely efficient modulation, you know, 50 odd micron long, and in the O-band. So that's quite difficult to achieve with electro-absorption modulators in silicon, because you need a quantum confined Stark effect. So it's one quantum wells, and you need to match lattice and everything and reduce defects, right? But this is actually possible, and we demonstrated it, and that was done at wafer scale, and we got 100G out of this. So you know, it's showing that we can actually achieve that. And we can transfer the light from high index to low index with about 1.5 dB insertion loss and low reflection. So next slide, please. So the obvious next task is, okay, so if you can do that with silicon germanium, you can do that potentially with 3-5 materials, and this is exactly what we did. So you can see that 3-5 materials, if you're on a laser on an amplifier on chip, is 3 or 4 microns thick, right? So you have to work with that. And how do you do it? Well, you use silicon nitride in the same way, and you try to adapt the mode and things like that, right? So next slide, please. And this is what we fabricated. So you have a device, you know, electrically connected in the middle here, and you have your waveguide and nitride waveguide on both sides. So this is what it looks like, and this is a cross section of the device. Next slide, please. And we got, you know, CW, you know, operation out of this, coupled directly to a waveguide. So you know, we got a few milliwatts, but we have like a couple of you know, iteration, you know, on the roadmap that will improve that, you know, dramatically down the line. And the next step is also to move that to a more stable 200 millimeter platform. So next slide, please. That's the CW laser in the O-band. And we also have like amplification here, which is the important part, I believe, in any systems. If you have switching or any complex system where you have like a lot of cascaded devices, you need something that enables to amplify your light as you go along. So lossless switches, you know, and so on and so forth, right? So again, here is just like an early demonstrators. We aim for like more than 10 dB, you know, amplification in the O-band, but you know, this is first demonstration here. Next slide, please. So what's next? Well, as I said, for us is really to drive like density of integration, but density of integration comes with you need a native light source, you need an amplifier. So how do you actually achieve that? And this was just like some examples of what we are planning. And down the line is how do you actually reduce the size of those big lasers, I would say, because they're 2 or 3 millimeter long. What do you do to drive integration further? And you know, try to target that VLSI type of system. Next slide, and that's my acknowledgement, and I will stop there. Thank you.
All right. Thank you very much, Frederic. Great introduction, great presentation. And yeah, let me remind you that so we welcome questions to our speakers after each session. So if you have a question in mind, please feel free to push this raise hand button at the bottom of your Zoom screen, and then I pass you the word. And while you think about your question, I'll ask myself, Frederic. So this is, of course, a very interesting development, this heterogeneous laser that you can grow directly on silicon photonics. What is, you know, how reliable it is? How long did you test these lasers for? I wonder.
So we're in the middle of it. That's a very good question, actually. But you know, so quantum dot lasers have been shown to be quite reliable because the quantum dots and any defects that, you know, will go through like the dot layer will not really affect the performance. So right now it's more about trying to find a way to grow it at scale, you know, and have it uniform on the 200 millimeter platform. And then we'll start looking at, reliability and things like that, because that comes with the epitaxy itself, right? So you have different tools to achieve that. This was done using MBE, but you can potentially do that with MOCVD, and we need to trade off the two platforms to achieve the best performance anyway. So yes, very good question, and one step at a time.
Yeah, but do you believe this kind of heterogeneous integration will, become available soon, so that we don't have to bother anymore with all the hybrid putting
Well, I'm
chips on
fighting.
chips, flip?
This is what I'm fighting for. And one of the big problems that I'm facing right now is to have the tools available to grow at 8-inch. Because as you know, all the 3.5, environment is really smaller scale, right? And it's really recent where people have started to actually invest in 300 millimeter tool, MOCVD, or even MBEs at that scale, because they're fairly expensive, and for research, it's a bit more difficult. But essentially, this is what we're working on, and we're trying to get those tools in order to demonstrate and validate those kind of platforms. Yes, so it's working progress.
Was it grown with MBE or MOCVD?
So this was an MBE, but we're looking for MOCVD going forward to be able to get this, selective epitaxy and.
Wow. Yeah. Okay. Yeah, because this is a really impressive development then. All right. All right. Do we have any more questions for Frederic? Just raise your hand and I pass you the word. Okay. And if not, then I thank Frederic again for this great introduction and the kickoff of our meeting. And I pass the word to our second speaker, who is Prem Jonala Gadda, the VP of Sales at the US, representing iPronics. Hello, Prem. Great to have you with us.
Hello. Can you guys see my screen? Let me just where is it? Just give me 1 second. Okay, cool. And let me put it in full screen. Okay, is that good?
Yes, you're good to go.
All right, yeah. Good afternoon, everyone. And if you're like me in the Bay Area, California, a very early good morning to you all. Today I'm going to talk about optical circuit switches for AI data centers. That's what we do at iPronics. I think this is something that you all know. Don't need to explain too much here, but just to kind of set the context. As you know, the density of AI compute is increasing in terms of GPU dies per package, and also how many GPUs you can fit in a rack, and then how many racks you connect, right? So NVIDIA is executing phenomenally well with release of GPU every year, new generation of GPUs every year, and the density is increasing phenomenally. So all this networking for the GPUs, as you can see, there's stringent requirements on it, right? There's the networking within a domain for computation of these AI training workloads that is scale up, and then connecting all these domains together that scale out. So lots of requirements on networking. And one of the biggest challenges as you scale the AI clusters is reliability. Any sort of errors in the network, either it's coming from GPUs or from the network itself, can drastically affect your training or inference performance, right? And then there's also needs for reconfiguring these AI clusters because every training model requires a certain type of traffic pattern. So you should be able to reconfigure this AI cluster on the fly. And so all of these requirements are there, and all of these requirements are being put on the AI data centers in a very power limited and a space limited conditions, right? So we don't have as much power to power all of these things up, and neither do we have as much space. So any solution that's going to solve these problems should be power efficient and space efficient. So, so how do we solve these requirements, right? So any solution that's being developed needs to be cost effective and mass producible, right? So if it's not cost effective and mass producible, it cannot get used in AI clusters. And because of the power demands, low power consumption is also quite important. And reliability, of course, anytime there is a failure, it's going to affect the workload, so it needs to be reliable. And reconfiguration should be fast, not only just the ability to reconfigure, but it needs to be fast. And we solve all of those things using standard silicon photonics. That's how we do it. So what do we exactly do? We actually build gain-controlled optical circuit switches that are low power and high performance. We have built a bunch of IP in Ipronics, which we use to kind of build these optical circuit switches. As you can see on the slide, there's the photonic IC, and then we also build all the necessary software and control electronics that need to go along with the PHIX and the system itself. So this is an optical circuit switch that is built using standard silicon photonics technology, which consumes very low power, and it also has amplification. So any loss you may encounter using the silicon photonics waveguides, you can actually compensate. So looking at what we have done so far and what we will be doing in the future, at OFC this year, we demonstrated our optical networking engine 32, which has 32 ports, and that is sampling to customers since Q2 of this year. We have a 64 port version, 128 and 256 port version on our roadmap. The system itself, as you can see, has the silicon photonics chip. It has all the control electronics. It has the optical amplifiers, and it's a 1U box for the 32 by 32. It's quite the feat. The PHIX itself has over 2,000 programmable unit cells, we call them, which are basically the Mach-Zehnder interferometers. And then we have about over 4,000 actuators, in total around 10,000 components on the optical subassembly. So quite the fascinating device, and it's sampling to customers, and we have a roadmap to double it next year and then the years onwards. So another interesting thing about our device is it needs to work with existing optical devices out there, whether it's pluggable transceivers or near packaged optics or optical interposers, or even co-packaged optics. So you can actually take the fiber from all of these optical devices and connect them to the optical circuit switch that we're building, and you can achieve the optical networking goals that you have, right? So using the optical circuit switch, you can actually reduce your link cost, because you're actually removing a couple of transceivers and potentially an electronic switch in the middle, right? And we also have all the telemetry that is needed, as well as the link gain. So that helps with deploying this switch in more places. And we also have under a millisecond reconfiguration time. So that's also helpful for AI workloads. One of the concerns people would have when you are looking at silicon photonics based optical circuit switches and optical amplification is the impact on the bit error rate. And so this is measured bit error rate on our 132 device across the O band, the full spectrum. And as you can see, it's pretty flat, and sometimes the degradation is, less than 1 decade. So it is in the range where it's not going to affect the link operation. So in summary, we've been using silicon photonics to build these devices, which allows us to build an optical circuit switch that is cost effective. We believe it will be lowest cost per port. The ability to mass produce these devices and have high reliability. Other optical circuit switches may use movable parts. There's no movable parts in this one. So that's going to help with reliability. And because we have optical amplifiers, we can bring the optical loss to 0. And we also have system telemetry and compact devices, about 1U rack for the 32 port. And we can try to keep it the same for 64, depending on the connector and so on. And of course, fast reconfiguration. So all of these aspects will help make this optical circuit switch very suitable for AI data centers. So with that, I will end my presentation and hope this was useful. Back to you, Ivan.
Thank you, Prem. Thank you, Prem. Great presentation and very interesting developments happening at iPronics. So yeah, please go ahead and raise your hands if you have a question for Prem. And in the meantime, I am wondering myself, so do you have any forecast for the amount of demand you can get for this kind of devices?
Yeah, so I think, we are sampling this device to our customers and they are doing evaluations. One number that's out there that's kind of public and published by other optical circuit switch vendors is in 2030, they believe this market would be about $2 billion of TAM. But we've also heard that it could be much more than that. But the most conservative number that we have seen is 2 billion TAM in 2030.
Okay, that's very impressive. There are a couple of questions in the chat. I see we have one from Philip at Bay Photonics. Philip, would you like to ask it? You can unmute yourself.
Yes, thank you very much. Yeah, hi everyone. Yeah, the question is the idea that you keep a lot of the optical processing in the optical domain, a bit like OTN, optical transport networks, kind of would like, and therefore, is there like power savings, less electronics dissipating power, and therefore it's better for the environment? That's the question.
Yeah, that's absolutely right. So all of the processing of light is happening in the optical domain using the silicon photonics PIC. So the PIC itself consumes really low power. I mean, there is some power that's used for the electronics that is driving, and also most of the power consumption comes from the optical amplifiers. So other than that, it's an all optical domain circuit switch. There is no electrical to optical and optical to electrical conversion happening on the system. So that's what helps keep the power consumption quite low. Yeah.
Thank you very much.
Thank you.
I see there is another question from Noel at SAIS. Noel, would you like to ask it?
Hi, Noel.
Okay. Well, he's just wondering if it's actually an open platform or proprietary. Yeah.
Sure. Yeah, the platform, I mean, the technology that we use to build the silicon photonics PIC is standard silicon photonics, but proprietary. The ability to pack that many programmable unit cells into a single chip is our IP and our secret sauce. But the platform itself is open in the sense the software APIs are open. Actually, in July, we started a sub-project in the Open Compute project for OCS. And this OCS sub-project in OCP will actually help standardize all the interfaces into an OCS and create an open set of APIs into the platform. So the idea is anybody can kind of interface with the platform in terms of configuring it, as well as getting the telemetry. So the platform itself is open from that perspective. Yeah.
All right. And one more question from Guillaume from Merck. How does it compare to the other types of switches, and what are the key advantages?
Yeah, I'm thinking especially of free space switches.
Yep, excellent. So a lot of the technology in the optical circuit switching space has been so far free space and using MEMS. That's the most predominant one. And it's very different from that in the sense the light is actually going through waveguides on the PIC and manipulated through our programmable unit cells. So it increases the reliability extremely high, right? Because there's no moving parts, and the silicon photonics process is quite standard. So reliability is one. Of course, cost is another one. So because we're using standard silicon photonics, we're able to pack a lot more ports into a small PIC. And so cost also goes down. So I would say higher reliability, lower costs are the key advantages compared to other optical circuit switching technologies out there.
Okay, so if we don't have any more questions for Prem, I suggest we thank our speaker once again for this great presentation. And I welcome now the first speaker of the session, Cor Scheppens, CEO of Photon. Welcome, Cor. And Cor will talk about photonic interposers with embedded chiplets to boost AI performance. And the floor is yours.
Okay, thank you. You can see my screen, or?
Yes, indeed.
It's full screen?
Yes. You're okay. Good to go.
Good. Let me try to find this one as well. Good. So yeah, thank you for the introduction, and I would like to use the next few minutes to tell a little bit more about photonic interposers and how they can be used to scale photonics to volume, and also how it can boost potentially AI performance. So suppose most of the audience is aware of, let's say, the copper interconnect bottleneck at data centers, and specifically when you're using AI algorithms, it becomes more prominent. And photonics is a solution there. And it really requires photonics to grow to higher volumes. And what we see is actually still, we believe, kind of a hidden problem. And that is that the accurate placement of photonic components needs to be quite accurate. And well, it can be done, but it really requires dedicated tools to do that. Usually something like a micro tool. It's really slow and does not scale. So on top of that, it's also quite costly. And well, if your system becomes more complex, the active alignment that's used becomes also very impractical to be used. So we don't think that that's a good way forward. We need a solution that does scale. And what we want to propose is really use, let's say, the existing die-attach tools that are out there for electronic components. They usually have like 3 to 10 micron accuracy, and we want to use those. And there's a large variety of tools available, ranging in different speeds that they can run at. And what we do at Photon is that we add an auto-alignment layer to the interposer. And whenever you have like within the 10 micron accuracy, this structure will guide your die to a more accurate precision in the range of 100 nanometer. That's in essence what we do. Obviously, that goes a lot faster, and the standard tools making it much less costly. And we're really looking at cost of sub-dollar cents. That's really a target that we have. So on top of that, we also came up with an improved way of doing edge coupling and can get really low loss there. And yeah, on both of the topics, we have filed patents. So yeah, if you look at that, obviously AI market is booming and it's going like crazy, I would say. And we see that billions of dollars are being spent in developing the best chiplets out there for this particular case. And there are well-funded startups like AL Labs, Light Matter, Celestial, that are trying to get into that market. And obviously all the big guys are also working on that. But so far, we've not really seen a good solution to do the placement at a scalable way. And if you look at what we do, yeah, it's going to be low cost and low loss, and that gives you more possibilities. So you can do another trade-off, either use a very large PIC with a low yield, or use divide it into many small PICs and with a much higher yield. That might be a much better cost trade-off. And yeah, moreover, we are able to integrate different types of photonic or even electronic chiplets. So that gives you much more flexibility and architectural freedom, which also can give you an additional performance boost. So if you look at the technology, I'm not going to show you the patented technology here, unfortunately. And there are many different types of integration schemes possible, but here's just one example. So here we start with a standard electronic interposer, which has through silicon vias and some RDL layers. And yeah, we put a photonic layer on top of that. So there are some waveguides, the alignment structures not shown here, and there are cavities where the dies will be placed at. So you see here a top view of the interposer, where there are quite a lot of places where you would need to place the PHIX. And obviously we do that then with these standard die attach tools. So you get an electronic connection at the bottom, and the waveguides are coupled at the edge of the chip. And yeah, finally we can also hook up a fiber either with a grating coupler or edge coupling. So that's in essence what we do. As the topic of today is on AI, let's take a look at an example from an AI solution here. We'll look at a Blackwell GPU. It has an electronic interposer, not a photonic interposer yet. But yeah, it's made by TSMC. TSMC is doing a lot of interposers, and they have 3 flavors, and the last one is called CoWoS L, and that is also used for Blackwell, along with a co-packaged optics solution. And if we look at that, here's kind of a cross-section of that, where we have the CoWoS layer, which, let's see if we can get a laser pointer. So it's basically this part here, where there are some simple chiplets integrated into a molded part. So that's the black part. And then it's, let's say, wrapped with some RDL layers at the top and at the bottom. And that's basically the interposer as it's done nowadays by TSMC. And then we have on this side here, we have a PIC with a driver which is bonded on there with at wafer level. And yeah, that's a chip that's going to be placed on the substrate inside the package, on the edge of the package, basically. And there you also hook up a fiber, either again with grating coupling or with edge coupling, as it's shown here. But what this still gets is like we have short wires for the HBM that's connecting here, but for getting from the GPU, which is called logic here, to go to the EIC, it's a longer path, and that is requesting some more power, and might also impact some speed with going through all of those micro bumps and then some larger bumps on the substrate. So what we propose here is that you could add a photonic layer actually to this interposer. And so it's here it's done partly, not on the wall interposer, depending on what the need is. And then you move this PIC and its driver into the interposer as well. And in that way, you can shorten that path between the GPU and the EIC, and potentially get some speed increase and save definitely something on power. Besides that, it also makes the package somewhat smaller. So, but that in itself might not be enough to justify the cost of adding this photonic layer. So what else can we do? And here is another example that what we can do is just adding extra high bandwidth memory here. And that's then on a longer distance. So that has some more problems in the connection. But when we do this over a waveguide, we can go for this longer distance. And even more, we potentially can go at a higher speed, and we can also add more bits per cycle when we have bits multiplied over the waveguide. So that's certainly a benefit. And then there is a study out there that shows that when you quadruple the amount of HBM around the GPU, it can basically run larger matrix multiplications, and that would allow to halve the amount of data transfer that goes in and out of the board. And as that is your bottleneck, that could also significantly improve the AI performance. So, and obviously, if you have already this HBM going over a waveguide, then also the other one probably can be replaced as well, and using the same way of working. So that is basically what I want to show you today. So we have a photonic interposer that provides a path to high volume photonic systems, not just for AI applications, but can also be used for datacom or photonic computing or quantum computing. It's a simple, low cost, high yield solution. We don't need a lot of masks to make these, at least with respect to the photonic layer. And it's going to be low loss and high performance. So with that, I would like to conclude, and if there are questions, you can ask them now, but I'm going to be also at PHIX Summit this week, so if you're there, you can ask me in person, but you can also send me an email. Really appreciate the feedback that you have. So if you have an application, talk to us. If you're a supply chain partner who sees that you can add value to this, let me know. And in case you're an investor, we're still closing our round now. So if you're interested, you can still get in. Thank you for your attention.
Thank you, Core. Yeah, very interesting developments and actually interesting paradigm shift that PhotonPoser offers in this domain. I'm wondering, so you mentioned the representatives of the value chain. So what kind of people actually you could benefit from partnering with?
Well, obviously, we're talking about standard die attach tools. So I'm already in discussion with a few of them, but always interested to hear from others as well. And yeah, there are more things in there. We're also looking at nano imprint solutions. So in that case, that can be done. Yeah, well, we have to make still a proof of concept for this. So yeah, clean room access is something that we need. So anyway, and that, of course, obviously the applications from customers are the most important ones.
Okay, okay. Thank you, Core. I see there is a question from Mehdi from Proud Technologies.
Yeah, thank you. Thank you very much for a very interesting talk. I have just a quick question because you have shown a schematic where you have the PHIX interposer much closer to the GPU and HBM, so you are reducing the distances. But have you thought about the problem with the thermal coupling? Because your GPU is getting hot and hotter. Like it will be a lot of problem with the heat management, and there is already problem between GPU and HBM. So getting closer. Have you thought about that?
Yeah, obviously that is an issue. Let's say for the interposer itself, it's not really a problem, but obviously the photonic chiplet that goes in there, if it's silicon photonics with ring modulators, it's going to be very sensitive to that, so it needs to be taken into account. But at least I see that people are able now to get better and better in to control that, and yeah, there might be also coming up some new solutions that have less impact from the power. Ideally, you want to have also a very low power solution from the photonic side here, that it actually is saving power instead of adding power. And yeah, there are always trade-offs, and but yeah, it's obviously a thing that is a key concern here. And there are also some solutions that people are working on the thermal solutions. And if they come up, that might also relieve this here.
Yeah. I would be happy to talk with you later. Yeah, pleasure. Maybe have some solution.
Let's do that.
Thank you.
Yeah, I'll be keen on bringing you in contact, two of you. In the meantime, thanks again, Core, for introducing this interesting solution to us. And we switch now to the next speaker, who is Amol Delmade, the Senior Photonics Engineer and the Product Strategist at Pilot Photonics. Welcome, Amol. And Amol will talk about multi-wavelength laser sources for scaling data center capacity. Whenever you're...
Thanks, Ivan. Yeah, I'll share my screen. Can you see my slides?
Yeah, you're good to go.
Yeah, okay. Hello, everyone. I'm Amol Delmade from Pilot Photonics. So we are a Dublin-based in Ireland SME company which develops a full stack photonic solutions for telecom, space, and wireless applications. So today I'll be talking about multi-wavelength laser sources for scaling data center capacities. Now you have all been hearing about AI applications and all, and how it's impacting the data centers and capacity inside it. And the reason we are here is how the photonics is leading the next wave of data center capacity growth. So this is a typical architecture of a data center. I think previous speakers also mentioned about it. So we have racks of the compute data. So there we have a servers which are like say compute GPUs, and then there are ASIC switches, and then these GPUs are connected with each other. That's a scale-up network. But there are multiple racks inside each data center, and that's a scale-out network. And we need to have a connection in the scale-up as well as scale-out networks. And also now recently, few companies are talking about a scale across network. That means connecting one set of this data center with multiple similar units, which are either placed in the same place or they are placed further away with a couple of kilometers or hundreds of kilometers. But that scale across concept is more or less similar to the traditional DCI networks, I will say. So co-packaged optics is, and there are other technologies which are also leading in how optics can help to improve the performance inside the data centers, reduce its power consumption and all. So, so just okay, so Pilot Photonics is working as a part of the consortium EU project, which is developing the full place CPU solutions for data center connects. Pilot is responsible for developing the laser sources as a part of that project. So in that project, we are advocating for the CPUs at the both scale up and scale out structure. So at the top of the rack, we will have a smaller, like say low speed as ASICs and with a lower number of CPU switches. And for the spine switch, we can have a, let's say 102 Tbps spine ASIC, and then we'll have more densely populated CPU switches there as well. So why CPO, or even few people are talking about NPOs as well. So CPU enables, like say, considerable power reduction in the data centers. So if you consider the traditional pluggable optics, that consumes almost 30 watt of power, because there is a long copper track going from the switch ASICs all the way up to the optical transceivers. But in terms of co-packaged optics, the silicon photonics is sit beside the on the same substrate beside the switch ASIC. So this length of the copper interconnect required is much smaller. So that helps to reduction in the power consumption almost by 3 times. And also how the speeds are increasing. So if you see the latest trend, so the Saturday speed are almost hitting 200G now. So that's, I think, Nvidia and Broadcom and other companies are already starting developing the products with the 200G SerDes. And if you consider the recent PEC or OCP or hot chips meeting, few companies are also looking at 400G SerDes. But there is a limitation on how much speed you can increase, and the optical speed per line is also scaling as the SerDes speed are increasing. But if you see our switch ASIC is like say almost hundreds of Tbps and all. So if you have to increase the speed, you need to go for parallelism, that is WDM kind of a solution. So there is a limited growth in the SerDes and per line optical speed. So there is a need for optical parallelism. So currently there are typically one or two or four lasers are used, but most of these lasers, they are O-band laser, but they are spaced almost 20 nanometer away from each other. So this is a typical wavelength span considered for the data center switching interconnects almost for all technology, but currently the lasers are spaced almost 20 nanometer. But if you have to go for more parallelism, so increasing the number of wavelengths and all, so you have to go much finer in the wavelength region. So there are a standard such as CW, WDM, MSS standard, which considers 800 gig, 400 gig, and 200 gigahertz channel as well. And they consider using 8 wavelengths, 16 or 32 wavelengths. And in this case, so there is a need for a densely spaced additional wavelengths are being considered for increasing the capacity. And Pilot Photonics is developing a couple of solutions to address this need. So, what are the typical laser source requirement for CPUs? So the number of wavelengths required are 4, 8, or 16. Then the spacing between those channels needs to be 200 or 400 gigahertz. There is, you can have a little bit slight, like say, fluctuation allowed on those wavelengths, but typically it's 200 or 400 gigs. The typical RIN is less than minus 145 dBc per hertz. Power should be around 15 or more than that. So these lasers need to support advanced modulation format signals such as PAM4 or PAM8. And as you can see, as I showed in the previous figure as well here, so the laser sources will be external to the CPU switch or entire, like say, ASICs as well here, because so currently we can use, let's say, nano ITLA. So if you consider current pluggable optics, so they use a nano ITLA lasers inside this. But if you consider using such nano ITLA lasers like say 4 or 8 beside each other and trying to put in this pluggable, it will be very difficult to manage that. So that's why you need to have a dedicated laser solutions designed for such application. And the main reason for keeping the lasers outside of the switch is ASIC or like the CPU switches, because it will help to decouple the thermal from the main switch ASICs chassis. Because if you, as you can hear from the previous speaker as well, they mentioned about the temperature thermal issues if we have the photonics very close to that. And especially lasers, the drift in the laser wavelength depends very, lasers are very sensitive to the thermal changes. So that's why this the industry is going toward using it as an external laser source in a ELSFP pluggable form factor. And it also helps to mitigate the premature aging by avoiding thermal cycling. Also, if something goes wrong with the laser, you can easily replace with just changing the pluggable module. So there is a projection from light counting. So as you can see, the demand for the laser will increase to almost a billion units as you move towards 2030, as the CPU switches are gonna go to tens of million. So there is a very huge growth requirement forecast in this developing just unique laser sources for this application. So small form factor external laser source in a pluggable is becoming a standard now. So as I mentioned, Pilot Photonics is developing a couple of laser solutions for this target segment. So our first one is a laser array PIC. So we have two different variants. So one is a DBR laser array and another is a DFB laser array. So this is our DBR 16 channel laser array PIC. So this is a standard form factor, or we have them in a staggered form factor as well. And this is our DBR laser array chip. So all the lasers are 200 gigahertz spaced. They are aligned with the MSA CW WDM standard. Each are capable of giving 15 dBm output power and less than minus 145 dB serine. So all these DBR laser arrays, they have a SOA attached to just get to the higher power. And they are excellent sources for IMDD system such as PAM4 and PAM8. So this is the spectrum of our laser array chip from the DBR laser array. And this is a package unit, and we are putting that in a pluggable form factor. So in this case, so this will be our laser array and there will be control electronics attached to it. So this is the one option we are having. The second option is for a coherent lasers. So even if you want to go to 32 or 64 lasers, so adding so many lasers in a single chip will be very difficult. So there is a requirement for higher densification with tighter channel spacing. And that's when the optical frequency combs come into play, because from a single device you can achieve so many wavelengths. And also if you want to go for let's say further increase the capacity for 400 gigs per days or even higher one, so you people might consider going for a coherent modulation inside the data centers as well. So so for such coherent modulation, the frequency and phase correlation also affects a lot, because that will, if your lasers are frequency and phase correlated, that will help to reduce the DSP overhead and power consumption. So that's when Pilot Photonics is developing a micro ring resonator comb sources. So we have a micro ring resonator which we can pump with a external laser source, and it will generate a multiple lines. But there has been some issues with because there are a couple of vendors available already in the market. So the major problem in using comb sources is the power per line and ring limitation. And that's when the Pilot Photonics patented technology come into play. So we use a combination of a comb source as well as laser array solutions. So we have a generator comb source using micro ring resonator, and then we feed that comb to a laser array unit. So that helps us to filter out the individual lines and boost the power. So the frequency and phase correlation will come from the comb side, while the power and ring will come from the laser array side. So that will help us to boost the power and performance. Just to give you an example, so we took one commercial micro ring resonator comb available. We filtered out an individual line and look at its ring. So you can see the ring in the blue curve, which is like say very high, around minus 122 dBc per hertz. But then when we put our one of the laser and filtered that one comb line and look at its ring performance, you can see that we achieve more than 15 dB reduction in the ring performance. And that helped us to give a much higher data transmission. So we were able to achieve 80 gigabaud PAM4 data transmission, giving 160 Gbps data rate. So this is a best solution for, like, say, if you want to increase the RIN and, like, say, have a minimum footprint just using the comb source, but and put it in. So we are trying to put this in a pluggable form factor. That's our ultimate aim. Then the third option we designed for is a benchtop laser source for testing. So this is just for R&D labs, and if you are developing some silicon photonics and you want a test source to use for testing that silicon photonics. So this has a 16 discrete DFB lasers in TO56 scans. So they are, like, say, Texar. So we can tune their wavelengths by thermally tuning. They have a tech as well, so you can monitor the temperature, and each laser you can, like, say, individually replace as well if you are looking for different wavelength configuration or if something happened to one laser. So this is a spectrum of those 16 channel lasers, and we can see the RIN of those lasers is also less than minus 155 dBc per hertz. So again, they are 200 gigahertz spaced aligned with the MSA CWWDM grid. We did some data transmission with, so we were able to achieve. So as you can see from this diagram, so we have a PAM8 transmission. So we did a 75 gigabaud PAM8 transmission with 8 wavelengths. So we are able to achieve 1.8 Tbps data rate. And also we did all with all 16 wavelengths with a PAM4 75 gigabaud, that is 2.4 Tbps. We couldn't move the data rate forward because of the availability of only one modulator to modulate all the 16 channels. But we are trying to procure more components to further show its capabilities. So these are the solutions for the multi-wavelength laser source, but there are few vendors which are still considering use of a pluggable transceivers. So those might be possible for scale out or scale across or DCI applications, especially if you go for LPO or LRO pluggables, because they can achieve a little bit lower power consumption and they will need just a tunable laser source inside. So Pilot Photonics has a tunable laser source as well. That's a nano ITLA in both C and O band form factors. So you can see we can achieve entire O band tunability just from a single laser. It's not a continuously tunable, it's tuned over every 50 gigahertz grid. And that's because the CPOs or this application requires every 200 gigahertz spacing, even if you consider any data center application. So this will be sufficient. So these lasers can achieve more than 13 dBm power. They have less than 250 kilohertz line width. The best part about this laser is we can tune from one wavelength to another wavelength in less than 10 nanosecond. So if you are looking for something fast switching of the wavelength with these devices, which can be also possible. And it supports the transmission of advanced modulation format signal such as PAM4, PAM8, QPSK, and 16 QAM as well. And we are currently sampling these units to customers as well. So if you are interested in, please get in touch with us. So just to summarize with a key takeaway, so there is a massive optical parallelism is required in scale up, scale out segments. Multi-wavelength sources in a pluggable form factors are suitable to boost the capacity. Pilot provide Pilot Photonics provides a few options to fulfill the market read. So we have a DBR, DFB options, which is best suitable for IMDD links options. Then we have comb source plus laser array for next generation of interconnect, so which can support higher speed, 400 Gbps or higher, or even if you're considering for going for coherent modulation inside the data centers. So if you have further questions, please ask me, or you can get in touch with me or through our sales channel as well. Thanks for your attention.
Thank you, Amol. Thanks for a great presentation and explaining very well what Pilot Photonics can offer us. I would like to ask you right away, so what the other members of our community can actually do for you? Meaning, where are you open for partnerships, and maybe where can you benefit from having our EPIC ecosystem around?
Yes, so we are looking for partnership because we have some of our, like the nano ITL laser, we are now sending to customers. So we are willing to test it with you. Even these multi-wavelength laser sources, again, we have packaged them and we are currently testing in lab. So if you have need, so get in touch with us and then we can work on together how to provide you that.
All right, all right. I see there's a question from Guillaume from Merck. Please, Guillaume.
Yeah.
Yes, hello. Thank you very much for your presentation. I have a question about a complementary technology. There's now a lot of multi-wavelength lasers. What about wavelength switching, wavelength selective switching? Are they ready for data centers? Can we just use what is available from telecoms?
I'll say it depends on, because I think the previous speaker from Ipronic also mentioned about, like, say, the way you can do wavelength switching is like, say, you can use the circuit switching as well as you can tune the wavelength from the laser as well. So so I will say this laser we provide, they are only fixed wavelength, but the DBR option, you can switch the wavelength by tuning the DBR section. But for the nano ITLA laser which we have, that you can use for switching very fastly, because our switching speed goes less than 10 nanosecond from one wavelength to another wavelength. So they can be used for switching as well if required.
Thank you.
Yeah. I think you're muted, Ivan.
Oh, I'm sorry. I was gonna say, yes, I hope that answers the question of Guillaume. And if there's no further question, we thank our speaker again. Thanks, Amol. And
Thanks.
pass the word to our next speaker of this session, Mehdi Nanmoun. He's a co-founder and the CTO of Proud Technology. And Mehdi will talk about diamond-coated EO multi-layer glass interposers for 3D system and package applications.
Thank you, Ivan. Thank you very much for the kind introduction, and good afternoon, everyone, or good morning, depending on where you are. Maybe I will start with a few words about Proud and who we are. So Proud is a spin-off from EPFL, founded 2 years ago. We are based in Switzerland, in Lausanne, which is the French-speaking part of Switzerland. And we are specialized in producing lab-grown diamond for high-tech application. So basically, we develop different kind of diamond-based solution. And today we are 7 collaborators in the company, so it's quite a small team. But we can count on different support from the Canton Vaud, from the FIT, from also EPFL as well. Let me grab some pointers. And also, of course, not last but not least, from EPIC Association. So maybe a few words about what we do, and it's all about diamonds. So I will just maybe take 1 minute to maybe explain or share with the audience that they are not maybe aware of the outstanding physical properties of diamond. There is many, actually. First of all, diamond is transparent, so it's very interesting in optical devices because transparency is quite in a large gamma or light broad spectra. It's based on diamond, so it's mainly based on the carbon atom, of course, so it's biocompatible, so a lot of potential for medical device. Then also there is very specific defect within diamond, but they are quite interesting for quantum and sensing application. And nowadays there is a lot of traction on that path because they are usable at room temperature. And of course, one of the most known features of diamond is the hardest material on Earth. So a lot of potential with cutting, drilling, but very much small technical aspects. And then there is maybe the 3 main aspects that they are in interest in within Proud is to use diamond for this capability or physical capability of dissipating the heat very well. So actually it's the best material to do that. So 5 times better than copper. Also, diamond can sustain very high voltage, so it's very interesting for power electronics. And finally, diamond can really be used in very harsh environment. So typically for space application, a diamond really has a role to play. Today, we will focus mainly on photonics and electronics for this topic, but I want also to talk about what made us actually within Proud Technology different from others is our ability actually to grow diamond on any type of semiconductor material without buffer layer. So as a result, you can really benefit from all this outstanding physical property of diamond directly, immediate benefit. So for example, for thermal dissipation, as this is really the focus on within Proud today, and the company is really focusing on tackling the problem of heat management for AI chips, because they're getting more and more powerful, but we need still to get rid of all this heat that are generated. This is really a game changer when we can really introduce diamond as a way to get rid of this heat. And if now we are really talking about what could be, also, as the question was mentioned, what we can offer to the EPIC community as well. So today, really, our solution is really to offer diamond for different applications, like but semiconductor and photonic platform mainly at different stages. So for power devices, also if you are looking for integrated thermal management aspect, or you want to integrate diamond and combine it with your own material, we can also work on that. And one thing we can also mention is like basically the diamond we are growing are electrically insulated, but also we can get very highly conductive layer just by doping, so can get even something close to a metallic transition. This is just some example of what some sample we have grown on different layer on different substrate. This is typically 0.5 to 3 micron of thickness, but it's always on customer request. So this is a bit about promotion of what we do internally, but it's also to give you a better overview before going really to the detail of the talk. So today I will really focus on the implementation of our technology for the photonic platform, and specifically for glass interposer for 3D SOIP application. And maybe I would just take a few minutes on the glass interposer. Of course, I'm not a specialist myself, but just to remind to everyone that, okay, glass interposer are just substrate that enable electrical interconnection of multiple ICs over shorter distance and with high input-output density, but also enables optical interconnection between photonic chips, and that consistently differ from standard PCB. But this is kind of a schematic. So you have a glass core material, and then you have different interconnection of the ICs. But one thing is like glass interposer, if we compare them with what you have on the market, it has some drawback. And this is was brought to us from another actually EPIC member, and thanks to EPIC for this connection. But we are now in contact with Postpac, and Postpac is a Finnish deep tech company that offer design and prototyping services. So it's a fabless company, and they are really focused on glass interposer, and they can offer different type of VS, also solder balls. And I think you have details on the slide, so you can directly contact Giovanni, which is the CTO of the company. But he approaches with a problem with this glass interposer, and we think at Prod that we can actually fix or tackle this issue, and mainly it's a heat problem. So maybe just a few words on that side. So the major issue is like we are going to get a multi-layer solution. So typically there would be like stacking or different chiplets and interconnection. So the complexity of a 3D IC design will be just exploding in the few years. And if we continue with a silicon interposer, which is already of course the material that's being used, it has its benefit as it has very good thermal conduction. But however, there is also very low bulk resistivity that affect the signal integrity. And on the other hand, you have glass interposer that exhibit excellent dielectric properties, but very poor thermal conductivity. So basically, our idea was, okay, why we should how we could combine actually the diamond layer or diamond layer with the glass interposer, so we can benefit from very high thermal conductivity of a diamond and integrate it to the glass interposer. So typically, our solution now it's really to be able to first bring actually this very high thermal conductivity of a diamond directly on the layer of the glass. So at different level, first one will be really to dissipate the heat horizontally among the RDL layers. So there will be a reduction of the local thermal gradient, which is also will be beneficial. Then we can really connect all the thermal VS just by having this thermally conductive plate. So at the end of the day, you will have less requirement on thermal VS, so less number of thermal VS, and also you will be lowering the area penalty. And also, as we will be also need to tackle the problem of the stacking, we will have let's say the need to also go interlayer. So really having the diamond inside the different layer of your IC. So also one thing will be also to go even on the backside of the power delivery network. So at the end, our solution, as we discussed also with Postpac, will be really to be able to make the glass interposer workable for the next generation of data center just by adding a superior thermal management thanks to the diamond layer. So this is just a few words. I cannot go much into the details, but we are, I would say, very open to discussion on that topic. We really want to get some help as well from EPIC members. It could be in different ways: technical support, pilot project, new ideas, co-development solution, and also, of course, if you have heard about grant proposal or funding, we are very much welcome to hear about that. And thank you for listening.
Okay, thank you very much, Mehdi. Indeed, a very interesting technology you offer with all the diamond substrate. Yeah, so if anyone in the audience can offer those services that Mehdi have listed, don't hesitate to contact him. I see there is a question from Core for the poser. Go ahead.
Yeah, thank you. Nice presentation, Mehdi. I saw you have like, it seems you can CMP your layer, but can you also etch it?
Yes, indeed, we can etch it. And we have all the processes to etch the diamond quite easily. So you can do patterning as well. Okay.
Because it obviously is also important to do. So, okay.
Yeah.
Good. Sounds very interesting. I think indeed we should talk.
Good.
All right. Thank you. Anyone else?
Well, okay. Maybe another one. So what is the required thickness of the layer that you would need to get really a good thermal dissipation?
So actually, we are always seeing the question the other way around. What's the maximum thickness you are okay that we grow on top of it? So usually it's between 0.5 micron to 1.5. It's a typical thickness we are requesting. I mean, people are requesting. And just to give you an idea, like with 1 micron, we can already reach 1000 meter per Kelvin in terms of thermal conductivity. So it's already quite high. Yeah.
Okay, good.
Yeah. And what kind of technique is used to grow it, Mehdi?
It's CVD. It's CVD technique. Yeah. So up to now we can do 6-inch, but we are in current development to go much larger. So and for glass substrate it would be even potentially panel. So quite interesting. Yeah.
Do you need to run it at a high temperature so that it's not compatible with some of the other steps that you need to do?
Yeah, actually, no, it's a very interesting question. Actually, that's also one of our strengths is we can do at much lower temperature, so we can preserve the integrity. So that's one aspect. Yeah.
Yeah, I guess you will affect the crystallinity. So if you go at a lower temperature, you might get not as good heat dissipation as well.
No. Anyway, the numbers I'm giving it's typically for thickness grown at very low temperature. I mean, very low. I'm meaning like 400 degrees C, 400, 500 degrees C. Yeah.
Okay.
Which is very low for CVD when you're growing diamond.
Yeah.
Indeed, very low. Thank you, Mehdi, and thanks, Core, for your questions. So with this, I'd like to pass the words to our last speaker of the session, Andon Bano. He represents Ficantech, and he's the head of the European sales. Welcome, Andon. Whenever you're ready.
Yeah. So, okay, can you hear me?
Yes. The floor is yours.
Okay. So, just a second. So, perfect. Now I'm sharing the screen. Now I should be all seeing my screen in full screen, right?
Yes.
Good. Okay, perfect. Yeah. So thank you very much, Ivan. I will make a quick introduction of myself. So I'm Andon Bano. I'm doing I'm working in the role of head of sales for the European region for Ficantech. I will spend So this is the outline of the presentation. So I will start with why AI is demanding and what is demanding from us as a photonics community, how photonics is becoming actually an everyday topic, how photonics is becoming, in just a second, I'm not, no. Yeah, I will just try to change. Yeah, now I'm using a microphone of my headphones. Sorry. I will start. So how photonics is becoming an everyday topic for all of us. Why automation is a way to go, and the SPI context naturally comes as an answer. And what is PhiContech doing to meet the market demands that are coming from the AI market? A quick glimpse of a product of PhiContech that go in line with this topic, and some closing remarks. So just for a quick introduction about PhiContech here. So PhiContech is a privately owned company established in 2001 in the north of Germany. So our headquarters are located in Aachen, near Bremen, in north of Germany. And yeah, we have our sites operating in Germany, US, China, Estonia, Ireland, Thailand, Taiwan, and Malaysia. So we're quite a worldwide company with more than 300 people. And quite a big part of it is working in R&D, which are kind of the biggest contributors to what I will show here today, and keeping up with the let's say with the newest demands all the time. We're active in different industries and different applications, starting from high power laser diode to cameras, sensors, telecom, datacom, where AI falls into this case. Let's say LiDARs, biomedics. So wherever there is photonics, there is actually also a PhiContech machine serving the market into automatic assembly and testing. We have more than 1,500 machines operating worldwide, and the number is growing quicker and quicker nowadays. And since 2010, we have an annual growth rate of 30 to 40%, which is more than the photonics industry itself as a whole industry. Now starting with the topic, I've here summarized a couple of data which should make us reflect and actually should push us to work more and more into this direction. So starting with the total capex that are being dedicated to the AI infrastructure, the number is roughly 500 billion in 2024, and this is growing much faster. This comes definitely with some power, with some energy consumption demand, which is expected to reach around 130 gigawatts by 2028. So what does this mean is that it doesn't only show an increasing trend in this field that we all of us know, and that's why we're gathered here today talking about this topic, but it actually shows that it's coming with challenges, not only photonics, but in other fields as well, like in this case where we're talking about energy. So if we would attend, let's say, similar events in the energy-related topics, most probably we'll see there that they are also dealing and discussing with similar, let's say, similar breakthrough changes to make this thing happen. But photonics is not only an enabling technology for this case, but it's also something that could release a bit of pain, because photonics is like could be actually the change that will be needed to make all the systems more energy efficient, most probably more cost efficient, but this not to just help the industry as a whole, but also to enable it to increase even faster, possibly, right? And here there is an estimation of annual growth rate that is expected in the global data center market, in the AI infrastructure, in the accelerator market, GPU, where NVIDIA, AMD, and so on are showing like growth rate, which is going tremendously fast, and also in edge data centers for low latency applications such as autonomous vehicles and so on. So practically, as a photonics industry, that we are considered as a key enabling technology for this industry. We should keep up with the same growth rate, and actually we're doing quite well. Now I will in this slide what I try to highlight here is actually photonics and AI. They are not anymore just technical niche topics. Now they are becoming everyday topics. So what you can see in common between the 6 articles that I've selected is that, first of all, there is a tech giant in these titles like AMD, NVIDIA, TDK, and so on. You can see the word photonics mentioned almost in all of them. And you can see that they are mentioned in journals, newspapers, or magazines, which are known to the popular market, not just to tech related people. So these are news from Reuters, from Financial Times, and from TechRadar, which actually are let's call them magazines or news portals dedicated to a broad audience, which means that photonics and AI is moving nowadays away from the technical niche that we're all common here to hear it for, and it's moving to the everyday use of every people actually, and that's a good news for all of us working in the industry. So my presentation will focus. So all the presentations before were focused quite in the technical breakthrough of photonics itself. As PhiContech, we are focusing on automation, how to make these things possible, and how to make these things scalable to meet the high volume demands that are coming towards us. But what are the costs of any technology actually? So here I've just broke down the total cost of ownership of adopting any technology. So we'll have some upfront development cost, some deployment costs, and then in the end, some operational costs to keep a certain technology up and running and possibly upgrading and following the market. We could work on reducing such costs by developing different partnerships, by having higher throughputs or higher volumes. Of course, the price per part will drop, by having a higher yield, so we have more efficiency in material usage, and by meeting industry standards. Certain industry standards are there exactly to meet certain quality, and also by making sure that our processes and our technology is scalable. And we believe that automation actually is key to all this and could help drive scalability from day one. So when we see cost versus time, of course, manual might seem more attractive because, of course, you might be able to do something in your lab with one person and a few tools. And then investing already from day one in automation might mean that you have to buy an expensive machine and probably like spend some time on it and so on. But over the time, this costs break even. So practically when you're at the prototyping level or maybe like product releases and so on, new product introduction, then maybe manual and automated costs will start to break even, because then you want to be quick in pivoting, you want to be reliable, you want to be repeatable and so on. And there is already a break even here between manual and automated. Even though the volumes are not there yet, you could start feeling the pain in the manual work when you're trying to be traceable, repeatable, and so on. Still in the low volume but high mix product. And then it's clear when it comes to high volume, the automation will have much lower cost compared to manual because it's scalable. And then by scalable, I mean that you don't have to actually hire a new person every time you want to, let's say, add a certain amount of volume to your production line. With automation, you have the know-how. Now you're just extending only the hardware to do that. So having this in mind, PhiContech is there to help customers starting with automation in mind already from lab systems. This is the machine types which we typically are serving the market, serving our universities, research partners, our let's say some startups, but also sometimes R&D labs within big players in the industry, right? So this is a machine which is made for prototyping, but with some production capability, but still in a semi-automatic way. You could use this to keep your IP internal, to make quick pivoting, to change your products fast, and to try things already to make them automated, proven from day one, right? So you don't want to develop something and then just discover later that you have to go back to the design or something like that just because it's not automatable. So this is to bring you into the topic of designing for automation. The second type of machines that we're offering is another, like increasing a little bit the level of automation. This is a closed door platform where you could already move into a batch production. It's made for production, for volume, but in the same time, there is some human interaction. You need an operator to prepare some trays, to load them, unload them, and keep the machine running. In the same time, in this machine, you'll kind of have some possibility to repurpose the machine, to change your products. Maybe not every day, like in the first machine, or every week, but still every couple of months, every few months. This is a machine that will allow you some development capabilities. The third level of automation is when you have a machine that has to be run always by an operator, and then here you can practically have a loader and an unloader, automatic one, and then you just prepare trays and load and unload them. And this is a fully operated operator around machine. The next step of automation that we want to reach, and actually we have reached at several industries, is the high volume manufacturing inline business. This means that this means that practically you could load only raw materials in front, and then you would get fully assembled and tested packages on the other side. We have done this already in the automotive industry, where the standards are quite harsh, and we have done this for LiDARs, cameras, and sensors for the automotive industry quite successfully. And we're ready now to develop the same path for the AI demands. And from this point on, I will show you a few technologies that we have been working on lately. This is, let's say, starting from what, in terms of photonics, what is AI demanding from us? What are these optical engines? What do they require from the technical standpoint? Starting from a wafer level, of course, wafer testers have been around quite some time in photonics as well. But PHIX this year just recently launched a double-sided wafer tester for the COUPE technology, where the electric chips are from on one side and the photonic chips are on the other side. And practically, you could do simultaneous dual testing within the same machine, but in a machine which is actually compatible with automatic test equipment, ATEs, standard ATEs, which OSATs and foundries are already familiar in the semiconductor industry. So I will run this video very quickly. The video is described, and this shows how, like, a little bit of the architecture of this machine. So there is a wafer table where the wafer is loaded, and then there is a ATE compatibility that comes from the top. This is important also, very important also for the, let's say, high frequency small signal analysis, when you want to do full characterization of the chip on the wafer level. And then from the bottom, it comes the 6-axis engines with the photonics active alignment for optical probing. And the optical probing then can be both edge and grating couplers. This is like unique in the world. This technology is serving the double-sided wafer tester. Of course, the same techniques can be applied for single-sided, both electro-optical or only optical testers at the wafer and the die level. What else is needed is like here I put another video where we show another, let's say, the other part of the value chain that PHIX offers. So we do not offer only testing, but we offer the full, from testing until the full packaging. So here you also see a few steps, dedicated steps that will have the optical assembly and testing for photonics and for AI applications. So let me press run the video. So first, this is just free space alignment of lenses or micro lenses in front of photonic chips or in front of lasers. This is active alignment process. The second one is FAU attachment, and then you'll see also some fiber preparation. So let me, so this is some FAU attachment. And this is a fiber preparation solution, so it's laser stripping, and then you'll see some connectorizing afterwards. So what PHIX is aiming to do is to give a full value chain, and as I mentioned in the automotive industry, we have achieved that by loading. So here's a fiber preparation, and so yeah. So what we achieved in the automotive industry by loading the raw materials, starting from the package, plastics, optics, sensors, electronics, all of the raw material up front, and then like having a packaged LiDAR every few seconds as an output, we want to achieve the same for the optical engines. What does this mean is that, yes, so far we can automate fiber butt coupling, we can automate free space alignment, we can automate wafer testing, but actually what we want to do is the connection between the cells, these machines, to be done in an automatic way. And for that reason, we want also to have this fiber preparation tool where you can put a spool of fiber, unspool it, strip it, cleave it, have prepared connectorization FAUs, connect them to another machine where you have where you can grip these FAUs and attach them to your chip and so on and so forth. So like this, you can go uninterrupted for a long chain of processes within the same line. And here in the next video, I'll just show you how we've been building a photonic line. This has been at PhiContech. We've been this is a relatively short line, I would say, for the automotive industry that we built, and we want to use this same experience actually in AI, and we are ready to do that. We have all the needed parts of the photonic value chain in that sense. So the line is being first manufactured at PhiContech, and then tested there, and then taken at the customer side for another test before it's ready for high volume process. But we are not only enabling the AI technology with photonics, we want also to make use of AI. And here is just an example that I wanted to give. So practically, we want to improve, as a general scope, is to improve the OEE, the overall efficiency of equipment efficiency of our machines or of our lines. And when it comes to high volume, this is very important. And you can improve it by reducing the downtime, by improving the performance, and by improving the quality of the products that are coming out, so the yield. And we have come up with machine learning algorithms which can act as for preventive maintenance, but also for process optimization. What does it mean is that the machine will be equipped with sensors, with a separate PC, which will be monitoring all the data coming from the sensors, from the axis, from the vision, from all the tools of the machine. And while monitoring them continuously, the machine might automatically recognize, let's say, an axis is vibrating more than usual, or an axis is not being able to reach the certain speed that has been doing in the past, and so on. So like this, you can prevent a failure by already intervening, and the machine will slow down itself and will call for assistance. So we're using AI actually to increase the lifetime, but also, like as I said, the OEE of our machines. And this is very, very important when you talk about high volume manufacturing. And of course, we're using tools like digital twins and so on to go for let's say, as training tools and so on, so our customers can have full digital experience and full digital experience on our machines. This is what I call a horseshoe. So this will for you will receive the slides and you will get a big picture of what PhiContech can do. I showed you a few videos. Those are just some few recent developments, but PhiContech is able to offer you automated solutions starting from wafer testing and fabrication, from wafer testing and hybridization to die level testing, assembly, hybridization, combining different technologies, lens and FAU fiber attachments, but also fiber preparation, as you saw in the video, and also end-of-line testing. So practically, you will have all the assembly and testing cells that you will need for your final product. It's a German technology with some international footprint. We have strong R&D team, a big global service and support team, which is actually continuously growing, because as our database of machine keeps growing, machine base keeps growing worldwide, also our service engineers, service and support team has to keep the same pace. We have already more than 1,500 machines delivered worldwide, and more than 400, or roughly 4,000 6-axis aligners delivered in the field, which is like a proprietary technology of PhiContech for active accurate alignment. And all of these technologies are served by the same software. So one software serves them all, which means you can reduce the, let's say, the training efforts on your team when you adopt PhiContech technology. We will help you, as mentioned before, starting from an MPI tool to develop the process together, have a test vehicle, go to a production tool, some training, and then be ready for high volume manufacture. And this way, together with PhiContech, you could reduce the time to market when you're scaling up and when you have a plan for scale up in the near future. We have additionally, I would mention here, upgradability and future-proof technology, which means that let's say one example here shows a machine which is capable to start with 100 G up to 1.6 tera transceivers that has been in the market. So our technology is made to be future-proof, and we guarantee that by following a modular approach which makes your investment future-proof and lowers your total cost of ownership. Here I will summarize with a few takeaways, which, starting from the beginning, I wanted to highlight that photonics is a key enabling technology, which means it has to keep up with the technologies which is enabling, which in this case is the AI topic. So AI is having a tremendous demand, which means photonics has to keep up with this demand. Automation, we believe, is key to reduce costs, increase volumes, and meet quality standards. And early adoption of automation will help you also have an easier adoption and easier scale up. PHIX will help you and will offer you a value chain starting from wafer to die to module level, both for assembly and for test. And we are a strong partner starting from product development, MPI, up to high volume manufacturing. So with this slide, I will close, and please feel free to ask me any questions. So this is a map of our presence worldwide nowadays. Thank you very much.
Thank you, Andon. Great presentation. Yeah, it's fascinating to see how fast the PHIX grows, how much impact they have over our industry. So I wonder if there is any questions for Andon about the PHIX machines.
It's the last presentation, right? So
yeah, maybe everyone is already tired. But if not, let me ask you myself. So what's the next step for PHIX? So now you can test wafers on double side. What is how can you foresee the further development of photonic integrated circuit testing machines?
Yeah, so in terms of testing, as mentioned, we came up with this double-sided wafer tester, but that's not the only thing that is needed, right? So we are open to explore different, let's say, different collaborations. Our aim is to be industry agnostic. So in that case, we have had collaborations. So the first tester was launched with Teradyne. Now we're collaborating with Advantest. So we want to make sure that our foundries and our OSATs, our partners, they can, let's say, they can choose PHIX independently of what testing technology they are used to. So this is like something that we are currently working on. But as mentioned also during the presentation, wafer testing is only one of the, let's say, only one of the bottlenecks that this field is facing. Let's say fiber preparation is nowadays heavily a manual work. And then when you scale up in chips, you have to scale up in the number of fibers that have to be attached to such chips. So then practically we are also working hardly into coming up with fully automated fiber preparation solution to be then combined with our assembly solutions as well. So this is currently, let's say, what we are working on. And of course, what we're looking for partners as well to collaborate. You might have heard also about the collaboration with Southampton, let's say, it's another example for laser trimming of chips on wafer, which is also a very good advancement. And that is also a next step into yield improvement of our processes. So yeah, things are moving in the right direction, but of course we're open to inquiries, but not only, also to partnerships.
Okay. Well, thank you very much, Andon. So with this, I guess we can close up our session. So you'll see right now the poll to give us some feedback about this meeting. This is very valuable for us. And let me share just a few quick messages with you. So this was the EPIC Online Technology Meeting on Photonic Chips for AI for you. I'd like to thank once again all the speakers of today's session: Frederic, Prem, Kor, Amol, Mehdi, and Andon. You all made this meeting very special, and we all learned a lot, I'm sure. So if you have any further questions or you'd like to partner with any of the speakers that you heard of from today, don't hesitate to contact me, and I will be glad to put you in contact with them. So also these online meetings just to give you the taste of how our offline EPIC meeting work. This is a very efficient way of building the collaborations and building a new network inside our industry. So the next occasion where you can meet us offline will be on 17th of November 2025 in Munich. This will be a special EPIC meeting co-aligned with the Semicon Europe that takes place as well in Munich, and we have a special co-host as a Munich-based company, Atacube, and a very interesting session representing a lot of speakers from both photonics and microelectronic industries. That includes XFAB, for example, and Besi Group, ASML, and ZEISS. So yeah, so don't miss the opportunity to join us and bridge the gap between the microelectronic and photonic industries. And with this, I would like to also remind you that EPIC is there to support you with technology, market, networking, marketing, mentorship, recruitment, and investment opportunities. And thanks to my dear colleagues for making this meeting possible. And thanks to all of you for your attention today. Thank you very much, and see you all on the next occasion.
Thank you. See you in
Thank you,
Munich.
Ivan. Thank you, Ivan.
Thanks, Ivan. Thank you.
Bye.
Bye.
Thank you. Bye-bye.
Thank you very much indeed, everyone. So the room will stay open for a few more minutes in case you have something to discuss in between each other. Otherwise, thanks all of you for joining. Thanks, Prem, for waking up so early to join us.
No worries.